Hello. Purpose of today's video is to review some of the properties of exponents and how they're applied to working with number. So all of these are basic skills that when you go further into mathematics, if you have these skills, it makes life easier for you. If you don't, it's going to make life very difficult. So basically, we want to become comfortable with exponents and how to work with exponents. So to start off with, we have the skills of writing as powers of 2. Basically, every one of these numbers can be expressed as 2 to some power. So obviously 4, for example, is 2 squared. 1 over 4 would be 1 over 2 squared, but that's not a power of 2, that's a power of 1/2. So 1 over 2 squared is the same as 2 to the negative 2 power. So 2 to the negative 2 power is the same as taking 2 and dividing it twice. So that's what 8 is 2 cubed, therefore 1 over 8 would be 2 to the negative 3. So you can start to see a pattern here. For example, if 32 is 2 to the 5th power, then 1 over 32 should be 2 to the negative 5th power. 2 is obviously 2 to the 1. I should put the 1 power there. I seem to have forgotten that. 1/2 is 2 to the negative 1. 64 is 8 times 8, which is 2 cubed times 2 cubed, or just 2 to the 6th. You didn't have to show all that work, but that's how I remember 64 as a power of 2. It's just 8 times 8, and then I can work backwards. And if 64 is 2 to the 6th, then 1 over 64 is 2 to the negative 6th. If 128 is just one more power, that's going to be 2 to the 7th, and therefore 1 over 128 is 2 to the negative 7th. Following on then with the same sort of patterns, this is the same exact thinking, the same reasoning, except this time it's 3 to a power. So 9 is 3 squared, 1 over 9 is 3 to the negative 2. 27 is 3 cubed, 1 over 27 is 3 to the negative 3. 3 is 3 to the 1, and 1/3 would be 3 to the negative 1. 81 is 3 to the 4th, 1 over 81 is 3 to the negative 4th. So hopefully you start to catch a pattern here. 1 as a power of 3 is 3 to the 0. 243 is 3 to the, or 81 times 3, so that's where I got 3 to the 5th from, and then 1 over 243 is 3 to the negative 5th. So you start to see a pattern here as to how we work with negative exponents and powers and so forth. Now we're going to start applying some of the other rules, like the product rule, the quotient rule, power of a power, power of a product, etc. So here, for example, we have 2 to the 1 times 2 to the a, and so essentially when we multiply, we're counting up total number of factors of 2, which in this case is 2 to the 1 plus a. So that's the product rule in general terms. 4 times 2 to the b is really 2 squared times 2 to the b, and we multiply numbers of the same basis. We're counting up the total number of powers of 2, which is 2 plus b total powers. In case you're not sure if you're doing any of these right, notice they're all expressions that have constants in them. We can replace those constants with variables and write them in as functions. So I put in y equals 4 times 2 to the x, and I got a graph of an exponential growth curve, no surprise. And I also put in y equals 2 to the 2 plus x power, and see I only see one graph here. The blue graph is on top of the red one because they're the same exact function. So that's how I know I did my work right. This should be applied to any of these exercises where you're not sure, or you can use a calculator, any number of ways of checking. I'm intimidated at first by letter, where even am I right now? I'm only on the second one. We're on letter C. I was intimidated by H, but we'll get to that one a little later. For part C, it's 8 times 2 to the t, which is 2 cubed. That's how I write 8, and so that's 2 to the 3 plus t. Now we get into part D, where it's power of a power. Some of these problems are exercises. There's more than one way to look at it. For example, I could take 2 to the x plus 1 squared and think of it as 2 to the x plus 1 times 2 to the x plus 1. Then I can apply the product rule, which says if you multiply two numbers of the same basis, you add the exponents. So x plus 1 plus x plus 1 is 2x plus 2. This is using the product rule to simplify. Or I could just multiply the exponents. 2 times x plus 1 is 2x plus 2, and that's using power of a power. So you don't have to do these two different ways, but it certainly helps if you do two different approaches and get the same result. This is a way of actually supporting your answer without having to use technology, for example. Letter E says 2 to the 1 minus n to the negative 1. I'm going to go straight to power of a power there and multiply 1 minus n times negative 1, which gives me negative 1 plus n, or n minus 1, which looks nicer. So that's using power of a power. You want to use the same concept. We can use the definition of negative exponents to say that means reciprocal, divide by the base. Then I could actually look at 1 as a power of 2, that's 2 to the 0. And now I see two numbers of the same base. I can apply the quotient rule, which says if you divide two numbers of the same base, you subtract the exponents. 0 minus 1 minus n, distribute the negative, and we get the same exact result. So this way I use the definition of negative exponents and the quotient rule. This way I shortcutted it and just used power of a power. No matter how I sliced it, I got with the same result. So once again, ways of checking your work. You can use technology to check your work, or you can use two different properties of exponents. If you can identify them and know that they're different rules and yet still get the same results, then you know you're getting a deeper understanding than just a bean counter approach. Moving forward, should be no surprise, either of these exercises here, I change 4 into 2 squared and then subtract the exponents. That's no biggie. Here, two approaches. The first one is the quotient rule, where you subtract the bases. Here's where you got to be careful. M subtract negative m is really m plus m, which is 2 to the m. And once again, another way of checking your answer is to try a different approach. I know that 2 to the negative m is really 1 over 2 to the m. 1 over 2 to the m is really 2 to the negative m. I'm sorry, 2 over 2 to the negative m is really 2 to the m times 1 over 2 to the negative m, sorry. And 1 over 2 to the negative m is really just 2 to the positive m, because this means, divide. And 2 to the m times 2 to the m is 2 to the m plus m, or 2 to the 2m. So we got the same results using different rules, so that's again a way to check. In letter H, we convert everything to powers of 2, so 4 is 2 squared, and 2 is already a power of 2. Then I subtract the exponents using the quotient rule, and I get that result. Same can be said here. They're already in the same base, so I just subtract the exponents, which is no big deal. You got 2 to the x plus 1, subtract x is just 2 to the 1, so it's 2. What's interesting about this is it doesn't matter what I choose x to be. X could be a billion. 2 to the billion plus 1 power divided by 2 to the billion power is 2. 2 to the 101 divided by 2 to the 100 is 2. So it's common sense, really, when you think about it. There's 2 to the x times another 2, and then divided by 2 to the x. And those, 2 to the x divided by 2 to the x is just 1. So we divide those out, and we're left with 2. So using a different approach and getting the same result means I understand, not just know, how to get my answers. And finally, for the last one, we're going to look down here. We have 4 to the x over 2 to the 1 minus x. I change 4 to the x into 2 squared. Then I do power of a power, so 2 to the 2 squared, to the x power, is 2 to the 2x. And then we subtract 1 minus x, we distribute the negative, and simplify. All of these should be checked on your own, but for now, this is a way of checking your answers. Alright, single powers of 3, this is pretty much the same, so what I'm going to do is let all of these write themselves out, just like we did, and then you can choose to pause the video and make sure that you got the correct answers. The last one is the one I thought was most interesting, by the way, because it's got different bases. So I write 9 as 3 squared, and then I do power of a power, so I distribute the 2, and then I subtract the exponents. There I have to distribute the negative, and I get 3 cubed. So this is another one of those crazy situations where it doesn't matter what I choose n to be. If n is 1,000, or if n is 1, or if n is pi, it doesn't matter. This number will always be 3 cubed, or 27. Show you what I mean, I let n equal 3, and here we're going to get 9 to the 3 plus 1 over 3 to the 2 times 3 minus 1, which is 9 to the 4th over 3 to the 6th. Now I know 9 to the 4th is really 3 squared. That's 3 to the 5th, sorry. 9 to the 4th is really 3 squared to the 4th, which is 3 to the 8th. So 9 is 3 squared times 3 squared times 3 squared times 3 squared, or 3 to the 8th, and then over 3 to the 5th, and that's 3 cubed. So look, even if I chose n to be 3 or 7 or 15, I would always get 3 cubed in the end, no matter what. So that's the math magic here. The last set from the first page of homework for today included writing without negative indices. The word indices is the British way of saying exponents. And then the next section is writing in non-fractional form. So every expression should not have a fraction in it. Rather, it would just have exponents only. So ab to the negative 2 versus ab to the negative 2, whether we put the ab in grouping symbols or not. The first case, it's only b to the negative 2, then multiplied by a, which is really a times 1 over b squared, or just a over b squared. Here, on the other hand, it's both a times b is to the negative 2 power, which is really 1 over a times b squared, which is really 1 over a squared b squared. So in the, where am I? Oh yeah, in part C, 2ab to the negative 1 to the second power, we could use power of a product right here. In which case, we're going to get 2 squared, a squared, b to the negative 1 squared. 2 squared is 4, a squared is a squared, b to the negative 1 squared is b to the negative 2. So then I take that negative 2 and I move it down so there's no negative exponents. Now, taking the exact same exercise, except this time I'm going to work from the inside. I'm going to say that b to the negative 1 is really 1 over b, so I get 2a over b. And then when I square that, I'm going to get 2a over b times 2a over b, which is 4a squared over b squared. It's the same result I got over here, but using a different approach. So please, again, strive to understand, not just memorize, and look at alternative approaches than the first one you came up with. Also remember, each of these can be checked using technology. I'm not doing that here. I showed you how to do it, but this video is more about the answers than it is about how to check your answers. So, moving on to letter D. I got D sorted out up top here. It's going to be 9b squared over a to the 4th. Letter E. You could start by taking this b to the negative 1 and making it 1 over b, but that makes a fraction in the numerator. So to get rid of the fraction in the numerator, I multiply top and bottom by b. A squared 1 over b times b is just a squared, and then c squared b on the denominator. Letter F is pretty straightforward. What I did is I just took the b to the negative 1 and the c to the negative 2, and they just switched places. That's really what happened. Now to try to understand that, I'm going to look at letter H, which has a to the negative 2 over b to the negative 2, and I could just switch the places because that's what just happened over here, but try to understand it better. Understand a to the negative 2 is really 1 over a squared, b to the negative 3 is really 1 over b cubed. So to make this fraction a little nicer, I'm going to multiply top and bottom by b cubed so they cancel in the denominator, and then we have 1 over a squared times b cubed is b cubed over a squared. Now that, again, when you look at where we started and where we ended up, this negative power really means the base is in the wrong place. A is in the numerator, let's put it in the denominator and have a positive exponent. B is in the denominator, let's move it to the numerator and have a positive exponent. So negatives really mean bases are in the wrong places, yo. Moving on to letter I. Oh, sorry, second approach here. One way you could do this is you could use power of a quotient. That is to say, these are both negative exponents. Let's extract the negative exponent and just have a squared over b cubed. We know that a fraction to the negative power is just the reciprocal of that fraction, giving us b cubed over a squared. Same result. All right, the rest of the answers are going to be provided here. I'll only talk briefly about this one. Well, briefly, 1 over a to the n is a to the negative n. That's straightforward. 1 over b to the negative n is b to the positive n. Also straightforward. By the way, if you want to look at an alternative here, you could say 1 over b to the negative n is really b to the 0 over b to the negative n, in which case we're going to subtract the exponents using the quotient rule. 0 minus negative n, which negative negative is positive, it's b to the n power. Finally, the last ones are right here, so pause the screen and check out what you need to know. This video has already gotten really long, so thanks for watching, and I hope this was helpful. Have a good day.